Our project wanted to focus on air quality, and it's pretty interesting. The main research question our group wanted to focus on was how do daily AQI levels and the distribution of main pollutant types vary across seasons in major US cities in 2023. And to fully take on our research question, our group decided to break it down into 3 sub-questions. How do average daily AQI values and the proportions of days in each AQI category differ between spring, summer, fall, and winter? How does the frequency of different main pollutants change by season? For example, are ozone-dominated days more common in summer, while PM2.5 dominated days more common in winter? Are these seasonal patterns consistent across cities and regions, or do some cities show unique seasonal signatures? We also had a hypothesis for each sub-question. Average AQI values will show clear seasonal differences. Ozone will be the main pollutant more frequently in summer, while PM2.5 will more often be the main pollutant in winter, and seasonal patterns will not be uniform. To answer these questions, we worked with the data of daily air quality for major U.S. metropolitan areas covering January to December 2023, and we had to clean this data up quite a bit. Here, we removed unnecessary placeholder columns, cleaned and standardized column names, and renamed columns to be consistent throughout the entire project. Here we converted the dates into proper date format, removed any rows with invalid dates, extracted the month from each date, and then we also created a new column for the seasons. We cleaned and standardized the AQI category column to match official EPA levels. We fixed inconsistent spellings, and then we also cleaned pollutant names to be the same format throughout the project. And for the exciting part, our results. For EDA 1, it shows how much information is missing for each pollutant across the entire dataset, and we can see that PM10, which is around 27%, and CO, which is around 24%, have the highest missingness, followed by NO2, which was around 20%. And this is important because we now know to move carefully when dealing with those 3 pollutants as they had the most missing information. EDA2 shows that air quality clearly changes by season, and remember that AQI is air quality index, and a higher AQI number means worse air quality. Here we can see summer is the worst, winter is the cleanest, and spring and fall are in between, so this shows that air quality changes in a seasonal pattern. EDA3 shows proportions of AQI categories, and the main takeaway here is fall and winter had the highest proportion of good air, while summer had the lowest, as it had moderate and unhealthy for sensitive groups peak during this time, indicating poor air quality during summer. EDA4 shows the seasonal distribution of the main pollutants, and the main takeaway here is that ozone dominates during spring, summer, and fall, while PM2.5 dominates winter. We also see that other pollutants outside of ozone and PM2.5 stay relatively low all year. This shows that warmer weather leads to more ozone-driven days, and colder weather leads to more PM2.5-driven days. EDA5 shows the average AQI on days when each pollutant is the main pollutant in each season. So the main takeaway here is PM10 dominated days have the highest AQI, followed by NO2, especially in the summer. This shows that these pollutants are linked to the worst air quality. EDA6 shows the values of each pollutant across seasons. Each violin plot shows the range of each pollutant values and shows variability. The main takeaway here is ozone, PM2.5, and PM10 all have a larger range in the summer, showing more fluctuation, which points to more unstable and potentially worse air quality. Cooler seasons show a tighter range, meaning cleaner and more stable air overall. EDA7 shows average AQI seasonally for East, Midwest, and West regions. The main takeaway here is each region follow the same seasonal pattern as AQI rises from winter, peaks in summer, and drops in the fall. We can also see the Midwest has the highest, East has lowest, and West sits in the middle for average AQI. This means that even though air quality changes with the seasons, not all regions experience it the same way. EDA8 compares which pollutant is most common seasonally across 3 regions. The main takeaway is in the East, ozone dominates all but one season as PM2.5 rises in the winter. In the Midwest, PM2.5 dominates in winter, but other seasons show that ozone and PM2.5 appear in similar amounts, showing no dominant pollutant. In the West, PM2.5 dominates in winter and fall, whereas ozone dominates during spring and summer. Once again, this shows that each region has its own seasonal pollutant pattern, and AQI isn't the same everywhere. These findings answer all of our research questions and also supports all of our hypotheses. For the first question, we said that average AQI levels would show differences, and that's what we found. AQI does not stay the same across seasons, as summer consistently had worse air quality, while winter and fall had the most good days. Second question, we said that ozone would be the main pollutant in the summer, while PM2.5 would be the main pollutant in the winter, and that's what we found. This supports the idea that the type of pollutant determines how severe air quality can become. For the third question, we said that seasonal patterns will not be uniform, and that's exactly what we found. All regions peaked in the summer, but the levels were different. The Midwest had the highest AQI, East had the lowest, and the West was in the middle. Each region had different dominant pollutants too, and this supports our hypothesis as it shows seasonal air quality patterns vary by region, even though they all share a summer peak. Those were our findings, and that concludes our project.